Hello, and I welcome you all to the 8th International Conference in Convergence in Technology. This is Astra Rally speaking. This is a total of 4 members in our group, including myself. The other three members are Karthik, Anjani Devi, and Ruchit. So our project is Multirate LFSR and software testing efficiency. So what are the contents? The contents of the project are abstract introduction, existing methods, disadvantages, proposal method, advantages, results, conclusion, applications, and references. What's abstract? We present a novel multiple data LFSR MISR for high throughput based architecture that is capable of producing results in parallel across many clock periods. The power consumption of the chip during manufacturing batch may significantly exceed those of the final product. This increase in power consumption can be largely attributed to non-chip generation of extremely random test patterns and the resulting expansion delay. Controllability and observability measures are used by every single one of the most widely used automatic test patterns of reform. The proposal work introduces a binary architecture. This which designs can detect single structured faults in a combination of circuit. So, the introduction of the project. In order to increase the fault coverage of three weighted random test pattern generated by finding resistant faults, a generator is used to determine the weights assigned to pseudo-random sequences. The pseudo-random sequence is produced by the linear feedback shift register LFSR. Before diving into the specifics of that process, what is probability detection? The probability of detecting a fault in a randomly generated test pattern is defined as the frequency with which a random pattern resistant fault is discovered. These patterns are inserted sequentially to the test design scan chains (DUTs), which is design under test. The DUT's response are compressed using a response comparator of a multiple inputs image register in Excel. So the existing methods are the preferred method is LFSR, classical LFSR. So the existing methodology is classical LFSR. This classical LFSR, when given n number of inputs, it produces 2 power n minus 1 patterns at its output. As this technique generates patterns arbitrarily, it is called pseudo-random. This test pattern generator is unable to produce all zero pattern. We see the polynomial for a typical 4-digit external register here. This is a standard LFSR with 4 registers T1, T2, T34 and an XOR bit. Here is a typical MISR with 4 bits. It is necessary to divide the polynomial at CUT output by MSR polynomial for the MSR to function. The final piece is the golden signature or golden reference, which runs on as more as possible. This shown in figure 6. This is the basic architecture of the list. Here we are using the bit swapping LFSR rather than the classic LFSR. Let's take a layer. In this list, the bit swapping element serves as a test pattern generator where the MSR is adopted as RA. So here the MSR acts as the output response interface. According to the bit swapping LFSR, this bit may reduce its energy usage, making it an efficient choice. So that's the reason why we are using here bit swapping LFSR rather than the classical LFSR. So what is the disadvantage of this design? This design, when used for large design under test, occupies high area. So here we are being compromised in the area. So this would be the disadvantage of this method. So what's the proposal method? The proposal method involves using a LFSR and another has a circuitry both in a combined circuitry. By enhancing the correlation between the succeeding test patterns, many flaws that are otherwise undetectable by a multiple LFSR or MISR can be found. Correlation between successive test patterns could be improved by continuously supplementing values of inputs from a present state. So we are using here data flip-flops as the default. The design and the test can be tested by applying a test vector to its primary inputs, which will cause the faulty wire to be driven to the opposite value and have a ripple effect on the device decision on the test principal outputs. Testing the capacity to control any net within the design from the primary inputs and observe the values of the any net within the design through the principal output is considered extremely challenging for a system which with asynchronous feedback and extensive fanning elements. So this is the proposed test architecture. Here we can see the LFSR and MSR combined together. We use to select the functionality of this circuitry. Let's say the mux is equals to 0. The LFSR is activated, and when mux is equal to 1, the MSR is activated. Method is carried out in three stages. The first stage includes the input vectors for the design are chosen by means of Box-1 selection. In the second step, a non-zero or non-zero value is used as a seed to generate a large number of pseudo-random values. Here we are using a non-zero value. Unlike ATPG, the number of primary inputs and outputs in a logical list is not a limit on the number of scan chains that can be implemented. What's our advantages? This method of list gives us a design injectors of two operations, LSI and LSI, with the less power and delay. So, using this proposed method, power consumption is reduced and as well as the delay. These are the results of project in a graph. Here we can see the utilization of the circuitry, the utilization of LUT 1%, flip-flop 1%, IOS 10%, UFT 3%. Here are the periods and the clock periods obtained in the test. The transfer power is 2.188 watts. This is the results of the project. There we can see the random patterns being generated at the final output. In the phase one of the project, when you when we use the pitch mapping LFSR, the area consumption was 9 LUTs, power consumption was 3.52 watts, and the delay was 1.040 nanoseconds. In the phase two, when we combine both the LFSR and MISR, the power area consumption was 8 LUTs, and the power consumption was 2.188 watts, and the delay was 0.955 nanoseconds. Here we can see the significant decrease in the power and delay. So, what's the conclusion? The proposed BISP TPG is evaluated and validated at front-end and back-end chip-level VLSI design phases. The proposed BISP TPG is made more robust by this verification by being subjected to severe conditions encountered in actual VLSI design. So here are the references of the project.